So today we are going to enter the modern era of cryptography and talking about Diffie-Hellman key exchange, which is one of the most amazing things you'll ever see. For me, when I first saw this, I couldn't believe it, and I'm still kind of wrapping my head around it. But this idea is a pretty big idea, and it's still used today. So let's talk about what Diffie-Hellman key exchange is all about. So far in the class, we've studied, honestly, just two basic encryption schemes, affine encryption and the Hill cipher. And of course, we now know how to do these two schemes in any modulus that you want to. And these systems are known as symmetric or private key systems. And here's what that means. What that means is that your two users, Alice and Bob, have to first agree on a shared common secret key before they begin encrypting and decrypting. Okay, so Alice and Bob have to agree on a common key before they get started. And because Alice and Bob both possess the same key information, that's why it's called a symmetric system. And it's private, of course, because no one else is supposed to know the key. Okay, so while it's true that symmetric systems are not used for e-commerce, that's what a public system is for, and we'll do that next week or two. Private symmetric systems are really important in private entities and government agencies. In fact, the federal, our federal government standard for encryption is actually a symmetric system. Okay, so private key systems are still very important, but there is a huge problem in using them in reality. And here's the problem: you always have to assume, right, that Eve, the eavesdropper, is always listening in to Alice and Bob's communications. That's why we have to encrypt anyway, right? So how can Alice and Bob realistically agree on a secret key if Eve is listening, right? So how can Alice and Bob agree that, hey, we're going to use key, 73, if Eve is going to hear that, right? And so that's a big problem. So how can Alice and Bob pass a key to each other over a monitored open communication channel? Now, how can they do that? Eve is listening. So and the other problem is it's not realistic, because if they had a way to convey such a big secret safely, this is the dark alley analogy. So I'm going to meet you in a dark alley and I'm going to whisper the key to you. Then we don't need to encrypt anyway. I could just whisper my plain text message to you in the dark alley, and we don't even need to encrypt. So if there's such a secure way to do this, then we don't need to encrypt in the first place. We don't need to even have cryptography. So this is unrealistic. In real life, Alice and Bob are very far away. They might not even know each other. And so how can they create a key in secret over an open line if Eve is listening? This is a big problem. So this problem prevented many good private key systems from being used because there's no way around it until 1976, when two mathematicians at Stanford University, Whitfield Diffie and Martin Hellman, figured out how to do it. And this is known as the Diffie-Hellman Key Exchange Protocol, or DHKE for short. Okay, and again, it was established in 1976. That's a long time ago. But it's still being used today. It's a very, very, very smart thing. And the ingenious part about this is that Diffie-Hellman key exchange actually allows for Alice and Bob to create a common key safely and do it out in the open. They do it over an insecure channel. So this is kind of amazing. Alice and Bob can send their key data over an open line, yet still be able to establish a secret key. And they do it right in front of Eve, even in the presence of eavesdroppers. So Eve can watch them do this transmission, and then Alice and Bob will be able to create the key, but Eve can't, even though she just watched them do it. This is kind of amazing, okay? So let's get into this, and I just want to make one thing clear before we do. Diffie-Hellman key exchange is not an encryption system, okay? I cannot use this to take a message and then encrypt the message and send it to you, and then you decrypt it. That's not what this is. This is a method that allows for two people, Alice and Bob, who might be far away from each other, to create a common key across an open line. Okay? It does not encrypt messages. It creates a common key. in the presence of eavesdroppers. Okay? Now, what we're going to see next week or so is that you can start to use this idea to make an encryption scheme, and that encryption scheme is what's called El-Gamal. So when we talk about El-Gamal, it is modifying this for encryption, but Diffie-Hellman key exchange is for creating a key, not for hiding information. Okay? So now let's describe the Diffie-Hellman key exchange protocol. There are going to be some parts to this description that don't make sense right now, and they aren't clear why I'm doing it. Just sit tight. We'll look at these issues in a future lecture. These are really security issues, okay? But let's just do the math right now, okay? So Alice and Bob agree on a prime P. Now your first question is, why do they agree on a prime? Because there's secretly a security issue here that makes primes better. Don't worry about it right now. But you have to use primes for a security reason that's not clear to you yet, but will be. Okay? So Alice and Bob agree to use a prime P, and they make this information public. Okay? So P is known to the entire world. It is not hidden, so even Eve will always know what their prime is. That's okay. All right? That will not help Eve steal their key. Okay? And of course, in practice, P should be very, very, very large in order to thwart any brute force guessing. Okay? So Alice and Bob will do all their math mod P. All right? So when they agree to work at the prime P, they also agree to work with everything being done mod P. Okay? And Diffie-Hellman key exchange will create a shared secret key among the numbers 1, 2, 3 up to P minus 1. Okay? Here's how. When they establish the prime P, Alice and Bob also have to agree on a particular fixed element G mod P. They have to fix a number mod P, and that number mod P is made public. Okay? So two things are public: the modulus they work in, which must be a prime, and a particular fixed number mod P. All right? Now again, for security reasons, this element G must be picked in a very special way, but for right now, for today, don't worry about it. Okay? Don't worry about it. So far, this is Alice and Bob's key establishment data, and this data here is known to the entire world, okay? Their prime P and their special number G mod P, and everybody in the world knows this, even the enemy, okay? So here is what they do. Let me leave their public data on the screen. Here's what they do to create a common key, big K. So here's how they create a key, big K mod P. First thing Alice does is she chooses an exponent x, an integer exponent x between 1 and P minus 1. Okay? And the important thing is that integer exponent x that she chooses is secret, and she never shares it with anybody. Okay? So nobody knows what her x is. She chooses that in secret, and she never tells anybody. And then Alice computes g to the x mod P. She calls the verdict of g to the x mod P, she calls that capital A. Okay, and she sends that to Bob over the open line. So Eve will know what A is because A goes over the open channel. So everybody in the world knows what A is. Bob knows and Eve knows. However, Alice never tells anybody X. X is secret. Bob does the same thing. Bob chooses an exponent Y in secret, and he computes G to the Y mod P. He calls the result B, and he sends it to Alice. So everybody in the world knows B. Alice knows it, but so does the enemy, Eve. However, Bob never tells Y to anybody. Okay? Then Alice computes the key by here's Alice's key calculation. It's B to the X mod P. Now, she knows B because Bob told her that. Everybody knows B, but only Alice knows X. Okay? Only Alice knows X. And then Bob computes his key by taking A, which everybody knows. Eve knows it, but Alice also sent Bob A directly, mod P, but only Bob knows Y, right? So only Alice can carry out this calculation because only she knows X. Only Bob can carry out this calculation because only he knows Y, even though everybody in the world knows P and B and A. So here's the amazing part. The key that Alice computes is actually the same thing as the key that Bob computes. So they have generated a common key. Okay? Here's the proof. Let's go through the proof. All right? The proof, the important part is going to be at this middle equal sign. All right? So let's go through the proof. Then we'll pause and we'll do an example together. Okay? But here's the proof. What does Alice compute to do the key? Well, she computes B to the X. B to the X. And she knows X. And she knows B. What she doesn't know is that b is g to the y. She knows g but not y. So Alice can't do this math, but it's still true that b is g to the y. So b is g to the y, but by laws of exponents, g to the y to the x is g to the yx. But look, this y times x in the exponent up here is the same thing as x times y. They're just whole numbers. Y times x is x times y. So right here is the important equal sign, that g to the yx is g to the xy. And now you unwind it, but g to the xy is g to the x to the y. But g to the x is what a was, so this is really a to the y. Okay? But a to the y is what Bob computes, and so what Alice computes for the key and what Bob computes for the key are actually the same. Okay? So this is sort of stunning. They both compute the same thing, but they don't know why, right? Because Alice does b to the x, and she knows that's going to be what Bob gets, but she doesn't know why, because she knows that b to the x is g to the y to the x, but she doesn't know what y is. She has no idea what y is. Likewise, Bob can compute his key by a to the y, and he knows that a to the y is g to the x to the y, but he doesn't know what x is. So they can't do the math in the middle, but they do know for sure they get the same answer. That's kind of amazing. So you will likely need to read this many times before it sinks in. I had to. Let's take a break, rewatch this if you need to, and we'll come back and we'll look at a concrete example.